Hi, and welcome to Dr. V's AP Chemistry webcast. In this webcast, we're going to be discussing sigma and pi bonding. What I'd like to do in this webcast is first to talk about what a sigma bond involves, and then talk about what a pi bond involves, and then figure out the number of sigma and pi bonds when we have a Lewis structure. And finally, I'd like to tie pi bonding into the idea of resonance, which is an important idea in chemistry. Our focus is on describing covalent bonds, and there are actually several different bonding theories. So what I'd like to introduce is really a small part of what's called Valence Bond Theory. And this part of Valence Bond Theory tells us that covalent bonds form when orbitals overlap. So if we have a random orbital, say an s orbital, and then another orbital approaches it, as they get close enough together and their electron clouds overlap, that's what we mean by a covalent bond. So now the electron density is shared by both atoms. The more overlap you get, the stronger the bond will be. What I just showed you is really an example of what we call sigma bonding. When the orbitals overlap in an end-to-end method, we call this a sigma bond. So I've got an s orbital with an s orbital, they come together, the orbitals overlap, and the electron density is shared between them, and that electron density is right along the internuclear axis. Look how much electron density is between the nuclei of the two atoms. This is a sigma bond. So on the previous slide, I showed you sigma bonds forming between two s orbitals overlapping. I could have an s orbital overlapping with a p orbital, and I would also have sigma bond forming. Notice it's that end-to-end overlap, and the electron density is between the nuclei. That's really the hallmark of a sigma bond. In AP Chemistry, they're not really going to ask you questions about how a sigma bond forms. What you need to know is that a single bond in a Lewis structure is a sigma bond. Consider the molecule chloromethane. I have 3 carbon-hydrogen single bonds and a carbon-chlorine single bond, 4 single bonds, and therefore I can say that this molecule also contains 4 sigma bonds because a single bond is a sigma bond. And I can get that just from the Lewis structure. Our other main type of overlap is called pi bonding. This is when orbitals overlap in a side-to-side basis, and the most common example of this involves 2 p orbitals overlapping in a side-to-side manner. So this side-to-side overlap is what we call a pi bond. Notice that the electron density is above and below the nuclei of the two atoms as they come together and overlap. So there's really no electron density along that internuclear axis, and that's the hallmark of a pi bond. It's worth noting that the overlap not being directly between the nuclei means we're not getting as good an overlap with the pi bond as we did with the sigma bond. For AP Chemistry students, what you need to know is that a double bond contains 1 sigma bond and 1 pi bond. So if we think about the molecule formaldehyde, the double bond between the carbon and the oxygen consists of 1 sigma bond and 1 pi bond. We don't even have to draw it, we just have to know what it is. And then we have a sigma bond between the carbon and each of the hydrogens. Total for the molecule, we have 3 sigma bonds and 1 pi bond. I wanted to revisit this idea of the side-to-side overlap of the orbitals. The pi bond that forms is above and below the plane of the atoms forming the bond. It is one bond, so although it's got 2 lobes to it, right, the upper lobe and the lower lobe, that is considered to be one bond. And as I talked about before, the electron density is not directly between the nuclei, it's not along the internuclear axis. And so this overlap is not as strong a bond as what we see with a sigma bond. Therefore, it's important to note that the bond dissociation energy of a double bond isn't twice as large as the bond dissociation energy of a single bond, because a pi bond is not quite as strong as a sigma bond. Like I said, our main focus is taking a Lewis structure and figuring out the number of sigma and pi bonds present. So if we think about ethene, C₂H₄, and we draw a Lewis structure, we have a double bond between the carbons and then single bonds between the carbons and the hydrogen atoms. The double bond is 1 sigma bond and 1 pi bond, and all those single bonds between carbon and hydrogen are sigma bonds. So the total molecule has 5 sigma bonds and 1 pi bond, and we just need the Lewis structure to figure this out. Sometimes I like to look at the orbital overlaps and show those sigma and pi bonds, and that's what I've got here in this diagram for ethene. We have a double bond between the carbons, and so we have a sigma bond and a pi bond. And then we have sigma bonds between the carbons and the hydrogens. So we're showing the total 5 sigma bonds and the 1 pi bond. It's a very different arrangement. This isn't something that AP Chemistry students need to worry about drawing in a test situation, but sometimes seeing it helps to make it clear where this is all coming from. The other thing I wanted to mention was about rotation around the carbon-carbon bond. If we're looking at ethane, C₂H₄, we can get free rotation around the carbon-carbon bond, no problem. And no, I didn't make this graphic. But if we think about ethene, C₂H₄, which we were just talking about, if I'm going to rotate around that double bond, around the carbon-carbon axis, I would have to break that pi bond and then reform it. And so we don't see this rotation around the carbon-carbon bond in ethene. And no, of course, I didn't make this either. We should also mention triple bonds. If we have a triple bond in our molecule, that triple bond consists of one sigma bond and two pi bonds. So if we think about ethene, which is our simplest compound with a triple bond, the carbon-carbon triple bond contains one sigma bond and two pi bonds. And then we have two carbon-hydrogen single bonds, which are also sigma bonds. So total for this molecule, 3 sigma bonds, 2 pi bonds. And just for fun, let's look at the pi bonding in ethene. I've got the carbons and the hydrogens, see how they're all in a line. This is a linear molecule. And I've got single bonds between the carbon and the hydrogen on either end. And I've got that triple bond between the carbons. The sigma bond I've shown with a line. And then we've got the pi bonds at 90-degree angles to each other, trying to show how it's oriented relative to the plane of the screen. So if we try to rotate around the carbon-carbon axis in ethene, again, we'd have to break pi bonds and reform them. So we're not going to see that kind of rotation. But what's really nice about this representation is it shows the 2 pi bonds really clearly. And then we know we have the 3 sigma bonds as well. And now I want to segue into a discussion about resonance and how this ties into pi bonds. The benzene molecule is a classic example of resonance. We can draw these 2 equivalent Lewis structures for benzene, where the 6 carbon atoms form a ring. Each carbon atom is attached to one hydrogen atom, and then we have double bonds between every other set of carbons. And I can draw the left-hand version, or I can draw the right-hand version, and they're both completely correct. And really, they're equivalent to each other, except for the location of those double bonds. Lewis structures really don't get to the true nature of benzene, and it doesn't help us explain why all the carbon-carbon bond lengths in this molecule are the same. We do know from just looking at one of the Lewis structures that there are 12 sigma bonds and 3 pi bonds. But how can we use this to explain the resonance structures that we draw, where we know the real molecule is something in between both of these 2 structures? Let's look at this starting by just focusing on the sigma bonds. We have 6 sigma bonds in the carbon-carbon ring, and then we have an additional 6 sigma bonds between each carbon and its associated hydrogen. But because of the way this molecule is set up and the hybridization around each carbon atom has a p orbital perpendicular to the ring, and these p orbitals can do pi bonding, side-to-side overlap with each other. And this is really what leads us into another view, another representation. So one option is we can think about localized pi bonds. These 2 carbons have p orbitals overlap. These 2 have p orbitals overlapping. Here's another pi bond, and they're localized. And of course, we could draw this representation where those pi bonds were in different locations, but we still had 3 of them. And this is what our Lewis structures are sort of implying. But we think the reality actually goes one step further than this. Instead of having localized pi bonds, this pi bond belongs to these 2 atoms, and that pi bond belongs to those 2 atoms. We can think of this as all 3 pi bonds belonging to all 6 atoms, where they're delocalized. And those electrons, instead of being shared by just 2 atoms, the 6 electrons in the double bonds are now being shared by all 6 carbon atoms. And that spreads them out. It gives them more room. It lowers their energy. It makes the benzene molecule very, very stable. And because those double bonds are now being delocalized over all 6 carbon atoms in the ring, now we can start to explain why all the carbon-carbon bond lengths are the same and why the bond association energies are the same. Resonance is due to delocalized pi bonding. Oh, that's a really interesting thought, isn't it? Anytime we can draw multiple resonance structures for a particular molecule or polyatomic ion, we can view it in terms of this delocalized pi bonding. So if we look at nitrate, right, nitrogen's the central atom, we've got the 3 oxygens, a Lewis structure, any one of the resonance structures would say we have single bonds between the nitrogen and 2 of the oxygens, and then a double bond between the nitrogen and the 3rd oxygen. But that pi bond can delocalize over all 4 atoms and spread out, meaning that negative charge and those electrons in that double bond are spread out over 4 atoms, not 2. They're spread out more, lower energy. It's a more stable situation. So we get this resonance structure. We can't draw this adequately with a Lewis structure, but pi bonding gives us another way to visualize it. Now, again, this isn't something that AP chemistry students would be asked to draw, but just recognizing that this is another way or a more sophisticated way to describe resonance is really helpful. The electrons in those pi bonds, like I said, are shared by all of the atoms involved in the resonance structure. This delocalized pi bonding makes it more stable, makes it energetically more favorable, lowers the energy of the whole system. And this is why all the NO bonds in the nitrate ion are the same length. This is why all the NO bonds have the same bond association energy. Resonance is delocalized pi bonding, spreading that electron density all around the molecule. Let's just do a quick recap of what we've talked about in this webcast. Single bonds are sigma bonds. This is really the core of what you need to know. Multiple bonds contain sigma bonds and a pi bond. So a double bond is 1 sigma and 1 pi. A triple bond is 1 sigma and 2 pi. Make sure you know that so that you can go to your Lewis structure and determine how many sigma and pi bonds you have. And you need to be able to do that. That's an absolute skill. You don't even have to explain why. You just normally need to say how many. And you should know that resonance structures involve delocalized pi bonding, and we can use this to explain why all the bond lengths would be equivalent. All the bond association energies would be equivalent. Subscribe to my channel so you get all my latest videos and study chemistry every day. That's how you get better.